A simple circuit is a circuit with a load connected to a power source. In this example, 5 volts connected across a 5 ohm load. But circuits can have more than one device connected to a power source, and you can connect devices in two ways, either in series or in parallel. This video will explain series and parallel connections and the characteristics of these circuits. Series connections have devices connected such that there is only one path for current flow through the devices. Devices connected in parallel have more than one path for current. In a series circuit, current is the same in all parts of the circuit. I've added ammeters to measure the current coming out of the power supply and flowing into and out of R1, R2, and R3. And when we run the simulation, we see that the current through R1 equals 0.33 amps, or 333 milliamps. And the current through R2 equals 333 milliamps. And the current through R3 equals 333 milliamps. This is a characteristic of series circuits. Current is the same through all devices connected in series. Mathematically, we would write this as IT equals I1 equals I2 equals I3, and so on, because the current through R1 we call I1, and the current through R2 we call I2, and the current through R3 we call I3. Another characteristic of series circuits is that the resistances add. The power source sees the sum of all the resistors. Mathematically, we would say R total, or RT, equals R1 plus R2 plus R3, and so on. Ohm's law applies here as well. I total, or IT, equals V total, or VT over RT. In this example, VT equals 5 volts, and RT equals 5 plus 5 plus 5 equals 15 ohms. So IT equals 5 volts over 15 ohms, which equals 0.333 of an amp, or 333 milliamps. In series circuits, voltage divides up amongst devices. In fact, series circuits are often called voltage dividers. The simulator in Fusion will calculate the voltage with respect to ground at all nodes. In series circuits, the sum of the voltage drops across devices equals the total voltage. Voltage drops are a transition from higher voltage to a lower voltage. In this example, the voltage drop across R1 is from 5 volts to 4.5614 volts, or a transition of 0.439 volts. And the voltage drop across R2 is 4.5614 volts minus 0.438596 volts, or 4.123 volts. The voltage transition across R3 is from 0.438596 volts to ground, or 0 volts, which is 0.438596 volts minus 0 volts, or 0.439 volts. Notice the sum of the voltage drops across each device equals the total voltage. Mathematically, we would say VT equals V1 plus V2 plus V3, and so on. Another characteristic of devices in series is that the largest resistance will always exhibit the largest volt drop. Recall, devices connected in parallel have more than one path for current. A characteristic of parallel circuits is that each device in parallel has the same voltage across it. We can see in this circuit that each device is connected across the 5-volt source, and so each device has 5 volts across it. Mathematically, we would say VT equals V1 equals V2 equals V3, and so on. Current in the circuit divides up amongst the branches. Using Ohm's law, I1 equals the voltage across R1 divided by R1, which equals 5 volts divided by 220 ohms, and so I1 equals 22.7 milliamps. Similarly, I2 equals V across R2 divided by R2, or 5 volts divided by 470 ohms, or 10.6 milliamps. And I3 equals V across R3 divided by R3, or 5 volts divided by 180 ohms, or 27.8 milliamps. In a parallel circuit, the total current, IT, equals the sum of the individual branch currents. Mathematically, we would say IT equals I1 plus I2 plus I3, and so on. In this example, IT equals 22.7 milliamps plus 10.6 milliamps plus 27.8 milliamps, or 61.1 milliamps. The reciprocal of resistors in parallel add together as reciprocals. Recall, a reciprocal is 1 over a value. So, 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3 and so on. The reciprocal of resistance is called conductance and measured in Siemens, so we could also say that the sum of all the conductances in a parallel circuit equals the total conductance. In our example here, the total conductance, 1 over RT, equals 1 over 220 plus 1 over 470 plus 1 over 180, which equals 12.2 millisiemens. Taking the reciprocal of the total conductance, that is 1 over RT, will give us the total resistance of the parallel resistors, or 1 over 12.2 millisiemens equals RT, or RT equals 81.8 ohms. Since the reciprocal of the sum of the reciprocal of resistors in parallel equals the total resistance, the formula for RT is sometimes written as 1 over R1 plus 1 over R2 plus 1 over R3 and so on. RT equals 81.8 ohms in this example. Let's check this answer with Ohm's law. RT should equal VT divided by IT, or 5 volts divided by 61.1 milliamps, which equals 81.8 ohms, identical to our previously calculated value. Let's review what we've learned by comparing and contrasting series and parallel circuits. Series circuits have one path for current. Parallel circuits have more than one path for current. Current is the same in all parts of a series circuit. Current divides amongst all the devices in a parallel circuit. In a series circuit, the total current equals the current through I1 equals the current through I2 equals the current through I3 and so on. In a parallel circuit, the total current equals the sum of the branch currents, or IT equals I1 plus I2 plus I3 and so on. In a series circuit, voltage divides amongst all the devices. In a parallel circuit, the voltage is the same across all devices. In a series circuit, total voltage equals the sum of all the volt drops, or VT equals V1 plus V2 plus V3, and so on. In a parallel circuit, VT equals V1 equals V2 equals V3, and so on. In a series circuit, resistances add. In a parallel circuit, conductances add. In a series circuit, RT equals R1 plus R2 plus R3, and so on. In a parallel circuit, 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3, and so on. There is another commonly used formula for the special case of two resistors in parallel. It's called the product over the sum formula, where R total equals the product of R1 and R2, or R1 times R2, divided by the sum of R1 and R2, R1 plus R2. Up next in the series, we'll answer the question, what's ground in a circuit?